Okay, so our last chapter, chapter 12, looks at intermolecular forces. So intramolecular forces are forces within the molecule, and we've looked at that, like whether the bonds will be polar or nonpolar and with molecular geometries. But intermolecular forces, which is what this chapter covers, are forces between. So inter is between, intra is within. So what are the forces between neighboring molecules that hold them together? So we understand that there are three states of matter, right? Solid, liquid, gas. Obviously, gases are mostly empty space. They are not held together well, so we know they have very low intermolecular forces, very weak forces holding those molecules together. Whereas liquids have higher intermolecular forces, and of course solid we would expect to be the highest. So when we look at those forces holding the molecules together, we're going to look a lot at phase changes. So taking a solid, melting it to a liquid called fusion, or taking a liquid and going to a gas called evaporation. As we do that, as we go from solid to liquid to gas, we have to break those intermolecular forces. So if the forces holding the molecules together are very weak, they're going to have very low boiling points and melting points or fusion points. But if the substance has very high intermolecular forces, very strong forces holding those molecules together, then it's going to take a lot of energy to melt or fuse them or vaporize them. So we're going to look at the different types of intermolecular forces here. The first one is called a dispersion force, also called a London force, London forces. And these are in all molecules. So all molecules have dispersion forces. So this is kind of what I think of, it's like your baseline. This is in everything. And what this is an instantaneous, so in an instant, dipole. So if I looked at an entire molecule and how the electrons were distributed, because electrons are randomly in motion, or constantly in motion, right, that at some random moment, the distribution of those electrons could be lopsided, right? Even if it's not a polar molecule, at some instantaneous moment, because the electrons are constantly moving, the electrons could be lopsided. They could be more on one side of the molecule than the other. And that would create a domino effect, right? If the electrons are more on this side, then the neighboring molecule that pushes the electrons away, and then the neighboring molecule pushes those electrons away, right? So it's like this domino effect of having these very instantaneous, temporary polar molecules. But as those electrons continue to move, right, overall, it's still a nonpolar molecule. It's just in that instant that the electron density could be kind of unevenly distributed. So they're not very strong, I'll say that. They're weak forces, but they are in all molecules. All molecules have that ability to have their electrons sort of out of balance. And what I think makes sense here is the larger the molecule is, the more electrons it has, the more of a possibility that will be, or the more of an impact that could be. So this is going to be true when you have molecules with a higher molecular weight or molar mass. Also, it is easier to sort of have that imbalance of the electrons, or more impactful, I should say, if the molecule is elongated. So like in a chain, rather than like being in a clump. So this becomes bigger in like organic chem. So like you could have a 4-membered carbon chain in a straight line, or you could have carbon in a T, right? And the one that's in the chain is the elongated molecule, and it would be easier, more impactful to have that electron distribution instantaneous, create this dipole, and then affect the neighboring molecule as well. So that's what that means by an elongated molecule. That comes up more in organic chem. The second type of force we have is a dipole-dipole force, and this is in polar molecules. So this makes sense. This is when we are looking at polar bonds. So for example, if we had a hydrogen fluoride, right, we expect a negative dipole and a positive dipole. More of the electron density is going to be on the fluorine side because it's more electronegative. So those are permanent, right, because overall you have a very polar bond. Fluorine is more electronegative. And so this isn't in an instant. This is overall. This is permanent. And so you can imagine the neighboring molecule, the fluorine is going to line up next to a hydrogen, right? Oops, sorry, that was supposed to be an F. My brain was trying to do two things at once and it didn't work. So we're still going to line up positives and negatives, right? And so that will help create intermolecular forces, right? Those positives and negatives, they attract each other. So that'll hold the molecules together better when you have a polar molecule, because those positives and negatives can line up. All right, and so polar molecules, again, have a higher melting point and higher boiling point, because if they have higher intermolecular forces, it's going to be harder to change that phase from a solid to a liquid or from a liquid to a gas. So first example we come to here, it says two of the halogens. So, and by that we mean the diatomics. We have F2, Cl2, Br2, and I2. It says two of these are gases at room temperature. One is a liquid and one is a solid. And how do we know which is which? Well, in all of these molecules, the fluorine, chlorine, bromine, and iodine, the diatomics, they are all nonpolar, right? The fluorine-fluorine bond, that is classic nonpolar. With chlorine, chlorine, bromine, right? The two nonmetals are the same. Electronegativity difference is 0. So these are all nonpolar, which means they don't have dipole-dipole forces. That's not an option. So the only thing they have here is dispersion forces, right? Those instantaneous dipoles. So if we're looking at assessing, okay, which one is the gas, which one's liquid, which one's solid, what we talked about with dispersion forces is it's just going to come down to molar mass. So when I look at my periodic table, fluorine is the lightest. This is the lowest molecular weight or molar mass. So I'll put Mn. And then for the iodine, this is the highest molar mass. So what we can expect then is that the I2 is going to be the solid at room temperature. The fluorine, being the lightest, is going to be a gas. It said there were two gases, so chlorine would be the second gas. And then the bromine in the middle would be the liquid at room temperature. And that's in fact what we see when we look up their melting points. Now, this is only dispersion forces. So when it's only dispersion forces, what we look at is the molar mass. Again, iodine, if you imagine, right, all those shells of electrons, 5 shells of electrons, right, a lot of electrons, it's easier to create an instantaneous dipole of all of those electrons with so many more electrons, right? So you can have an imbalance on one side of the iodine that creates an imbalance in the neighboring iodine, right? So it's just this domino effect. Now, with the next example, though, we've got a bromine monochloride and iodine monobromide, and it's kind of similar question. One's a solid and one's a liquid, and how do we know which is which? So in this case, we're looking at the BrCl and the IBr, all right? And we won't worry about completing the octet. They're held together by a single bond. Now, both of these should be polar molecules. The chlorine is more electronegative than the bromine, so that's going to create a negative end. The bromine is more electronegative than the iodine. So if I had a sample of the bromine monochloride or the iodine monobromide, these are both going to have, they're both going to have dispersion forces, right, and dipole-dipole. So they're both polar molecules, so they're going to have the dipole-dipole forces because they're polar. But everything has dispersion, right? All molecules have dispersion. So which one would be likely to be a solid and which one would likely to be a liquid? And so since they're both polar, we go back to that dispersion force, right? And the iodine monobromide, more electrons here, heavier, higher molar mass. This is the one that should be the solid. And then the bromine monochloride, lower molar mass, this is the one that should be a liquid at room temperature. All right. Another example here of how we can use dispersion forces to kind of understand intermolecular forces is we have Ch2O, so carbon, double bond, oxygen, hydrogen on either side. And then the C2H6, we have sort of a double center here, 2 carbons, 3 hydrogens attached on each of those carbons. And it says they both have a molar mass of about 30 grams per mole. So the molecular weight or molar mass on these is both about the same. One has a boiling point of negative 20 degrees Celsius, the other one negative 88. Which is which? So if I look at the first molecule here on the right, the ethane, the C2H, the carbon-hydrogen bond is nonpolar, right? The electronegativity difference here is a 0.1, which is essentially 0. So the carbon-hydrogen bond is classic nonpolar. So in this molecule, the only thing we have are dispersion forces. All right, so only dispersion forces in the ethane. But I keep saying the wrong thing. In the formaldehyde, the Ch2O, in this case we have a highly electronegative oxygen, and so that's going to create a polar molecule. So we are going to have the dipole-dipole forces, and again, the baseline, we're going to have dispersion forces. So both of those forces are going to be present in the formaldehyde. So the intermolecular forces we expect are going to be greater in the formaldehyde. All right, so higher, and intermolecular forces I just always abbreviate as IF, right? Intermolecular forces. So the forces holding formaldehyde together will be stronger. So one of these boils changes from a liquid to a gas at negative 20 degrees. The other one does so at negative 88 degrees. So the negative 88 degrees boils first, right, because it's at a lower temperature. And the negative 20 degree compound boils second. So we're going to heat both of these molecules. Let's say we start out, both of these molecules are at like negative 100 degrees Celsius. As we start to heat them, when we get to negative 88, one of them is going to transfer to the gas phase. The other one stays a liquid. I keep heating, and then when I get to negative 20 degrees Celsius, the other one turns into the gas phase. So which is which? Well, the negative 88, right, that means that one boils first. It has the weaker intermolecular forces. The negative 20 degrees Celsius boils second, has higher intermolecular forces. So the formaldehyde has the boiling point of the negative 20 degrees Celsius. The ethane boiling point is going to be negative 88 degrees Celsius. Because again, there's only dispersion forces here, whereas with the formaldehyde, we have polar dipole-dipole forces, and in addition to that, we have dispersion forces. All right, so higher intermolecular forces means a higher boiling point. Lower intermolecular forces means a lower boiling point. All right. Then on the next page, our third force is when we have hydrogen bonding. And that only occurs when hydrogen is bonded to a nitrogen, oxygen, or fluorine. It has to be one of those three. So when we were looking at the HF molecule before, that would have dispersion forces, of course, dipole-dipole forces, and hydrogen bonding. When we look at water, right, also has dispersion forces, dipole-dipole forces, and hydrogen bonding. Another one here would be ammonia, right, the trigonal pyramidal. So again, anytime the hydrogen is bonded to a nitrogen, we're going to add our third force, which is hydrogen bonding. So molecules that have hydrogen bonding typically have the highest intermolecular forces, which helps us understand, you know, water is a very small molecule in terms of molar mass, 18 grams per mole, and yet it has a really high boiling point, relatively, 100 degrees Celsius, right? It's an incredibly powerful molecule. I mean, think of all the destruction it can do. So water, it's just always, I was like, always one of my most interesting molecules to me, because the intermolecular forces are so incredibly strong, but it only has a molar mass of 18, right? And that is because of this additional hydrogen bonding. So molecules that have hydrogen bonding are always going to be the strongest in terms of intermolecular forces. So we've got a set here. We've got 5 different compounds to look at. Boiling points are here. Let's look at the intermolecular forces in each one of these. So this is why knowing VSEPR from the last 2 chapters and how the structure would look, how the bonding is super important. So ammonia I've got drawn for you up here. So we know that the nitrogen trihydride, of course, all of these have dispersion. We expect it to be polar. Nitrogen is more electronegative, so we're going to have a negative dipole and then a positive, right? So we're going to have a negative end and a polar end. So this is going to have your dipole-dipole forces as well. And then also here is going to be the hydrogen bonding, right? Because we've got hydrogen bonded to a nitrogen. In the methane, the CH4, in this case, carbon-hydrogen bonds, classic nonpolar. The only thing we have here is dispersion, right? Nothing else. In the C2H5OH, the ethanol, we wrote a structural formula here so that we could see that OH is going to create polar, right? Because it's going to have a polar end. So now we're going to have dispersion. We're going to have dipole-dipole. And because that hydrogen is attached to the oxygen, we're also going to have hydrogen bonding. So all three forces are going to be present in the ethanol. When we get to vinegar, acetic acid, right? What I have here, the CH3OH, I'll draw it over here. You have CH3 and then what's called a carboxylic acid. So the carbon has a double bond to an oxygen with this OH group, not hydroxide. Ironically, this is it's not a base, it's a carboxylic acid. This is actually an acidic hydrogen, but you'll learn that in organic. But because we've got hydrogen bonding here, we also have a very polar end, right? Very negative end versus a positive end for the molecule. This one has dispersion, dipole-dipole, and hydrogen bonding. All right, and then the H2S at the very end, we have dispersion, of course, because that's in everything, but we also have dipole-dipole because that electronegative sulfur in the center, just like we saw with water up above, is going to have a negative middle and then electropositive ends, but no hydrogen bonding here because the hydrogen isn't bonded to a nitrogen, oxygen, or fluorine. So when I look at these boiling points, right, do they make sense? And methane with only dispersion forces, right, has the lowest. That makes sense. Then when we look at H2S, now it has dispersion and polar, dipole-dipole forces, so boiling point is going to be higher. The ammonia, which is, a really small 17 molecular weight compound, but because of that hydrogen bonding, right, it has a higher boiling point than even the H2S. And then when we compare the ethanol and the acetic acid, the difference here, the boiling point increasing, we're adding, we've got more over here in terms of this negative side. But we've got all three forces in there, dispersion, they're polar, and there's hydrogen bonding. So we can see here that in terms of our intermolecular forces, everything has dispersion forces, but if it's a non-polar molecule and that's all you have, your boiling point, those intermolecular forces are pretty weak. Boiling point, melting point, going to be really low. When we add to that polarity, boiling point is going to go up. And then when we add hydrogen bonding, again, boiling point goes up because intermolecular forces go up. So everything's additive. Everything has dispersion. If something's polar, then we add to that dipole-dipole forces. And then if something has hydrogen bonding, it's going to be polar, but it also will have those hydrogen bonding forces. So everything kind of builds. Now, ion dipole forces, we save that when we talk about ions dissolved in polar solvents like water. So some of the things that we can look at when we assess intermolecular forces, we talked about boiling points and melting points. Surface tension is another one. So surface tension is the energy needed to create more surface area. So essentially what that means is we're breaking the intermolecular forces of the molecules within the body of the liquid to create more surface. So imagine like having water in a graduated cylinder and pouring it into a bowl. Well, now we have more surface area. So the intermolecular forces in the water molecules in the cylinder, they have to get broken up to create that surface area. And so surface tension is just a measurement of the energy required to do that. All right. Then with viscosity, viscosity is the resistance to flow. So the stronger the intermolecular forces are, the greater the viscosity. And viscosity, I was kind of thought of like was the thickness of the liquid. So if the molecules are very strongly attracted to each other, they don't flow around each other as freely. So viscosity, of course, depends on temperature. Temperature, right, is thermal energy. So the higher the temperature, the more energy those molecules have, the better that they could break those intermolecular forces. Same is true with surface tension, right? Temperature has a big impact on breaking intermolecular forces. And then the last one here, the capillary action. So we've seen that like in a capillary tube, right? You can just dot a liquid with that capillary tube and the liquid is sucked up the tube. And it's not like you have to suck it up. It just sucks up the tube. That's the capillary action. And it's from adhesive versus cohesive forces. Adhesive, think of adhering. So when a molecule has high adhesive forces, it wants to adhere to the glass. So those are our high forces between the unlike molecules, the liquid and the glass. Whereas cohesive forces are forces between like molecules. So how much the molecules want to stay next to them, you know, other like molecules versus being with an unlike molecule. So when a liquid is drawn up a capillary tube, adhesive forces are strong. Right, but if it doesn't want to be sucked up the tube, then the cohesive forces are stronger. Right, so we can just sort of think about that. But the big thing here in this first video is understanding the three intermolecular forces. So we have our three. I'm going to go back to the front page. Dispersion, again, in all molecules, it's that instantaneous dipole, right? Temporary, it goes away. It's only in an instant. The electrons are kind of off. They're not they're unevenly distributed, and that creates a dipole effect. And this happens when you have more electrons. So higher molar mass, more dispersion forces are possible. In organic, you might look at a carbon like chain versus a carbon T or something like that. So elongated, higher dispersion forces. The dipole-dipole adds to dispersion. So this is when you have a polar molecule. So anytime that there is a true negative positive end because the sharing of the electrons between the two elements or in the molecule themselves. So this is why we looked at this with VSEPR. We got our VSEPR geometry and then we could understand whether the molecule would be polar or nonpolar. Well, if the molecule overall is polar, it will have dipole-dipole forces, right? And then the last thing is the hydrogen bonding. And if it has hydrogen bonding, as I mentioned, it will automatically always have dispersion because everything has dispersion, but it will also be polar, right? And so any molecule that has hydrogen bonding means that there's a hydrogen bonded to either a fluorine, oxygen, or nitrogen. And so molecules that have hydrogen bonding have dispersion, dipole-dipole, and hydrogen bonding. They've got all three. So I'm going to pause there for this first video.